Hi everybody, today we are going to learn about the unit circle and see how we use the unit circle to calculate a bunch of common trig angles. And the reason why you have to learn these common trig angles is because they show up all the time throughout the trig unit, and the sooner you memorize these, the easier the trig unit is going to become for you. As with all of the other trig videos, if you see something written in black or another color, it's probably just me explaining. If you see something written in red, that definitely needs to go onto your foldable. Tab number 4, common trig angles. Here we go. So first, let's start by talking about the unit circle. The unit circle is a circle with a radius of 1, superimposed onto the coordinate plane. And the unit circle is super useful because it helps us calculate the trigonometric ratios known as sine, cosine, tangent, cosecant, secant, and cotangent of any angle between 0 degrees and 360 degrees. Or if you're working in radians, from 0, actually let's do it on the other side. To 2 pi radians. And the fact that when you rotate around the unit circle, you end up back where you started, makes it a periodic function. So if I'm rotating theta degrees around the unit circle and then I get back to right where I started before I, start rotating again or something, the fact that I always get right back to where I started means that trigonometric functions are periodic functions. So they always, when you graph a periodic function or when you graph a trigonometric function, it always starts somewhere and then it comes back to that spot, So that means that it's periodic in nature or repeating. When do we use trigonometric functions? We use them all the time in the real world to model things in nature, population, stuff like that. So let's say I look at, I'm watching the waves come in, right? I see that the wave comes in, it crashes, and then the tide goes back out. And then a few seconds later, another wave comes in, it crashes, and then the tide goes back out. If I were to model, there was a ball on the wave or something, and I model the motion of the ball as it goes through this periodic function, I'm going to start here, and then I'm going to keep coming back to when the wave crashes on the sand. I'm going to keep coming back to when the tide goes out. I'm going to keep coming back to when the ball is all the way up here. I'm going to keep coming back to when the ball is just about to fall down onto the ground. So periodic functions trigonometric functions model the periodic nature of things in nature. It can model populations of species, right? So, as a population grows, let's say a population of rabbits, right? As it grows and grows and grows and grows and grows, and the rabbits have more and more babies, they get to a point where the food source can no longer sustain that many rabbits. So the rabbits start dying, and then the grass comes back, and then the grass comes back. And then all of a sudden, the rabbits hit a point where they're like, oh, wait, we can start having babies again because all the grass is back, right? So the periodic nature of populations is another application of trigonometric functions. So the fact that a trigonometric function is periodic is super duper useful for modeling real world phenomenon. How do we navigate the unit circle, right? So we navigate the unit circle by rotating theta degrees or radians from the initial side. So I start at the initial side, right, where the angle starts, and I rotate, theta degrees this way, okay? And the terminal side of the angle, right, like the other side of the angle, if you'll notice, intersects the unit circle at a point. And if I were to drop a little altitude down here, right, I would see that this creates a triangle. Let me pop this triangle out right over here so we can get a better look at it. Okay, this is the same triangle as over here, just blown up. We've got theta over here. We have a 90-degree angle right here, and we know that the hypotenuse here has a radius of 1. So I'm going to go ahead and label this 1. All right, so we've got a little bit of information here. If you'll notice, when we start here and then go over x units, this bottom of the triangle here is going to be x units long. Because if we were to write this as a coordinate, right, we would have x, y. It would be x units over and then y units up. So we can write this as a triangle looking like x, y, and 1. This is the power of the unit circle. So if you'll notice, we have our triangle, and we can remember our trig ratios from geometry, right? Sine of theta is equal to opposite over hypotenuse. And you can remember these from, what was the thing they teach you? SOHCAHTOA? Yeah, SOHCAHTOA. So right now we're talking about sine. Let's talk about cosine of theta. The cosine of theta is equal to adjacent over hypotenuse. And then the tangent of theta is equal to opposite over adjacent. And that's just referring to, like, in reference to theta, what side is opposite, what side is adjacent, and what side is the hypotenuse. So let's go ahead and label those. Hypotenuse, opposite, adjacent. So just as we talked about the connection between the cosine of theta and x, the sine of theta is going to correspond to y, so just remember that. And the reason being is because if I look at the sine of theta, right, and then I look at the triangle, the sine of theta is going to be opposite, which is y, over hypotenuse, which is 1. The cosine of theta is going to be adjacent, which is x, over the hypotenuse, which is 1. And then the tangent of theta is going to be opposite, which is y, over adjacent, which is x. So sometimes we use the shorthand sine of theta equals y, right? Because y over 1 is just y. Cosine of theta is x, and the tangent of theta is y over x. Okay? This is just going to be part 1. I don't want to have like a video that's like 7,000 years long, so tune in for part 2 in just a second.